Welcome to this lecture series in linear algebra. In this lecture, we'll look at an application of the things that we have learned so far, and let us recall what we need. So primarily what we need is the first isomorphism theorem. And what does it say? It says that if we have a linear map from a vector space V to a vector space W, then we can factor it out into two parts via this space V mod kernel T, which is the quotient space coming from the kernel of T, to yield an injective linear map, which we denote as T bar. The vertical map is the natural projection. We also saw a more general version of this fact, but we don't need that for this lecture. All right. So what is it that we are going to prove? Fix a vector space. Again, everything is finite dimensional, and fix two endomorphisms on it. Then we will be proving that the nullity of the composite, this is S composed with T, is at most the nullity of S plus the nullity of T. So nullity of the composite is at most the sum of the nullities. Recall, nullity is just the dimension of the kernel. Okay, so let's see how we prove this. First, we will say a little bit about that. So what is the kernel of the composite? This is, by definition, those vectors which die under the application of S and T. So just so that there is no confusion, I'll put brackets. So that's what kernel is, which just rewriting, we get that, which is same as saying those vectors such that T of V is in kernel of S, right? Saying that S of T of V is 0 means the same thing as T of V is in the kernel of S. So we have that, and thus this is nothing but those vectors which lie here, right? T inverse of the kernel of S, which is T inverse of the kernel of S. So that's what kernel ST is, and therefore what we want to show is that dimension of T inverse kernel S is at most dimension kernel S plus dimension kernel T. So this is our goal. Okay, how do we do this? So we have this linear map T going from V to V, and here we have kernel of S sitting inside it. So this vertical map is the inclusion map, which takes a vector to itself. Okay. Here we take its pre-image, T inverse kernel S, and here again we have the inclusion map. Okay. And this map is nothing but the restriction of T to this subspace. Maybe I'll write it a little better. Okay. So this is nothing but the restriction of T, and just so that there is no confusion, I'll write it as T tilde. So T tilde is nothing. It takes V to T of V. That's what T tilde is. And it is clear that this diagram commutes. So whether you go from here to there, whether you go from here to there or you go from here to there via this route, no matter what route you take, you will always land in the same thing. So this diagram commutes. There is no conflict. All right. Now, what is the kernel of this map, T tilde, meaning the linear map going from here to there? What is the kernel? So note that kernel T tilde is same as kernel of T, right? If something is in the kernel of T, then T of V is 0. And hence, of course, that thing lies in the kernel of S. So, okay, what I'm saying is fix V in kernel of T, we want to show that this guy is in T inverse kernel of S, which is to say that T of V is in kernel of S. But that is true because if V is in kernel of T, then TV is 0 and hence TV is in kernel of S. 0 is always in kernel of every linear map. So that direction is trivial. And now if we have something here, if V is in kernel of, what have I written? If V is in kernel of T tilde, then T of V is 0 and hence V is in kernel of T. So just note this. Maybe I garbled my speech a little bit there. I feel I did, but this is very simple to verify. And now apply the first isomorphism theorem to this map. We do not apply the first isomorphism directly to this, but to that. And if we do that, we get this factoring. And here we get an injective linear map, which we denote by T tilde bar. Okay. So it's now simply because this is an injective linear map, the dimension of this guy is at most the dimension of that guy. And thus we deduce that dimension of this quotient space is at most the dimension of kernel of S. But what is the left-hand side? The left-hand side is dimension of T inverse kernel of S minus dimension of kernel of T less than equal to dimension of kernel of S. And if you just rearrange these things, you get the orange thing, which is same as the red thing. That is what we wanted to prove. So that's it. That's a very nice proof of this fact. And I think this is all that I wanted to discuss. So just be mindful of these little maneuvers. If you directly apply the rank nullity here, you will not get anything of this sort, of course. It will not even involve the map S. To involve S, we had this. But even before applying, even coming up with all this diagram, we first understood a little bit about the kernel of the composite. When we landed here, then we came up with this idea that maybe it is best to pass to this subspace rather than work with the parent space. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.